Hello and welcome to Database Management Systems. I'm Javita Christie, and this is in continuation of my videos on storage strategies in DBMS, or as I'd like to call it, data structures in DBMS. And in this particular video, I'm going to explain B trees, which are a data structure that allow us to create multi-level indices. So first of all, I'd like to begin with what is a tree. And I don't mean a tree that grows outside. I mean a tree that is a data structure. So in computer science, a tree is a widely used abstract data type that simulates a hierarchical tree structure. It has a root value and subtrees of children with a parent node represented as a set of linked nodes. So trees are a type of data structure that allow you to create a hierarchy, which is written right here. So a hierarchy necessarily means that you have a parent, and then you have children, and those children have children. So when you talk about relationships like that, then it's a hierarchy. You could be talking about a hierarchy in a company or workplace. That would be also a hierarchy. There's a manager, and manager employs somebody. So there might be a deputy manager, or or a CEO. So those types of things together, they form a hierarchy. And a tree is a data structure which is used in DBMS in order to form this type of a hierarchy to store the data in such a way that you can access it very quickly. And so in a tree also, to understand it better, we always say that it has a root, and it has a parent node, and it has a child node. And the reason why we use these words is because it's a lot easier for human beings to understand these things in terms of relationships that they understand. So that is why a tree is represented as having parents and having children inside of it, and then they are linked together, and that's why you can say that it's a tree. Now, I explained to you what a tree is. Our next question should be, what is a B tree? In data structures, if you study data structures, you have lots of data structures available inside, and they are nothing but a technique of storing and implementing the data. And so there are several data structures available. There are stacks and queues and trees in particular are of many, many types. And the one that is used in DBMS is a B tree. So I'm going to explain what a B tree is. So first of all, it's a self-balancing tree data structure. Self-balancing means that at no point would it be growing only on one side. It would grow on all the sides. Sometimes you might see trees that are growing, and I'm talking about trees outside. You might see trees that are growing more on the left and less on the right. So this tree data structure is not of that type. It can balance itself by its own properties, because that's how you will create it. It allows searches, sequential access, insertions, and deletions. So you can, in a tree, in a B tree, you can perform searches. So you can search for a particular node. You can do a sequential access. That means you can access all the nodes if you want, starting from one, ending at whatever is your last node. So you can perform that type of an access also. You can do insertions. So at any point you can insert new nodes inside the tree. And you can also do deletions. So if you want to delete some node from your tree, you can do that also. And if you look at it now, you can see that it actually satisfies everything that you need to do in DBMS. You would like to perform a select query and search for certain data, for data that satisfies your condition. You might want to perform a select query and access all the data. So that would be sequential access. You might want to insert data into your table. That would be an insertion. And you might want to delete data from your table. That would be a deletion. And obviously, if deletions are allowed, then updation is not a big problem. Updation is nothing but, searching for the data and then just changing it. So if you can search, you can definitely update. So a B tree is well suited for storage systems that read and write relatively large blocks of data, such as disks. So in the previous video too, I explained that for a database to work, you need to bring data from the secondary memory, which is your hard drive, into your primary memory, which is your main memory or your RAM. And to do this, we require some storage strategy where a data structure is used because it makes your work a lot faster. And so whenever you have to retrieve large blocks of data, then this type of a B tree is very good. And once again, it's commonly used in databases and file systems. Now, if you haven't yet watched the video on indices, please go ahead and watch that, and then you'll understand this better, because in that video I explained some of the indices, and there were two types which I left out and I said I'd explain in the upcoming videos. So this is one of those two types. Now, whatever indices we studied before, they are all single level indices, and single level means there's only one level. So for example, if this is your instructor relation, then you might create a primary index on the ID column, and then you would store all these values inside. You would store all these IDs in your index, and next to those IDs you will store the address, the address on the disk of the entire row, and that's how you create an index. But it's only a single level index, and you don't see any problem with that. But what if I ask you to search for the ID 98346? So now what you have to do is assume that this is right now, this is an index, a primary index on the ID column. And now if you want to search for this particular ID, you would have to start from the first value. And when you look at the first value, you'll realize that this one is much larger than that. So you go to the next value, and then the next value, and you keep searching till you reach 98345. And then you realize that you've actually reached the end and you did not find this value, which means this value does not exist in the table. And when you're working with a DBMS, you will get these types of queries. It's not that people are always going to ask for data that is present in your system. Sometimes you might get a query for data that's not present. And at that time, if you're using a primary index, you would have just, a single level index, you would have just wasted time in comparing this index with all other indices in the hope of finding this. And in the end, you wouldn't even find it. And even if I was looking for 98345, I would still have to look for it from the beginning till the end. And there is an algorithm called binary search that starts looking from the middle. And that is possible in this case because the ID is in a sorted order. But you also know that we create single level secondary indices also, and in which case everything is not in a sorted order, and it becomes very difficult to search for something that is not present, or to search for something by comparing with each and every ID or each and every department name. So that is the problem with a single level index. So instead, you could form a multi-level index, which looks something like this. So the idea behind a multi-level index is that there are multiple levels, and the first level is where you start looking. But the first level contains only one block of data. So for example, if one block of data contains 100 records, then this is that particular block. So this first block is storing an index, and using that index, you're going to try to access the next block. And then using this, you're going to try to access the third block. And when you access block 0, when you access this first level, you will get to decide whether to go to the left side or the right side. So this way, you wouldn't have to search through the entire index. You would necessarily eliminate at least half of it, because after looking at this particular value, you'd realize whether to go to the left or to go to the right. And if you go to the left, you won't be seeing any values of the right side, because you know that you won't find your index value over there. So this is how a multi-level index works, and you'll understand it a little bit better with another better example. So assume that all these are IDs of employees, and they are stored in this manner. Now, if you look at it carefully, you can see that all of them are sorted. And by sorted, I mean on each level they are sorted within the level itself. So if you look at this, this is my first level or 0th level, where you can see that 30 and 70 are in sorted order. Then I have the next level where you can see 8 and 25, 40, 50, 76 and 88, they are all sorted. And then the last level also contains everything in a sorted order. You can verify that for yourself. And another nice property of this is that when you see a line, a connection, a link going from 30 to this node, you can see that on the left side of 30, everything is smaller than 30. So 8 and 25 are smaller than 30. Then there's a line going from between 30 and 70, and that points to values that are between 30 and 70, and you can see that right here. So 40 and 50 both lie between 30 and 70, and this is how you can see that these are values lying between 30 and 70, not just 40 and 50, but if you go one more level down, you can see that even all these values here, all 6 values here, are lying between 30 and 70. And then you can see that there's another line going from 70, after 70, it's going here. And all these values are larger than 70. So this is one of the properties of a B tree. And if you look at the next level, this type of a property is maintained. Everything on the left of 8 is smaller than 8. Everything between 8 and 25 is between those two limits, and everything after 25 is larger. And you can verify for 40, 50, and 76, 88 on your own. So this is what a B tree looks like. And now you can see how my search operation might become a lot easier. So for example, if I was looking for an index, let's say 26, then I would go first of all to the first level, and in the first level I would compare with the first value, and upon comparing I would realize that it is less than 30, and so now I know where I have to go. If it were to be greater than 30, then I would have to compare it with 70, but it's not. So I have to just go to the left side of 30 and go to this node and compare 26 with 8. And then I'd realize that it's larger than 8. So I wouldn't go to the left of 8. I'd go to the right and check it. And I will check with 26 with 25, and I'll realize that it is larger than even 25. If it was smaller than 25, then I would go down this road. But because it is larger than 25, I'm going to go down this link. And then after going down, when I match 26 with the first value, I'll notice that it is matching. So if you see it, I only had to make comparisons here. So I had to compare once with 30, then with 8, then with 25, and then with 26. So with just 4 comparisons, I was able to find this node. And that is the power of a B tree. You can make very few comparisons and find your node. And if the node does not exist, for example, if I were to ask you to search for 27, then after reaching here, you would have compared it with 28 and realized that there's nothing below it. And 27 does not match with 28. And you would have realized right there that 27 does not exist. So you just had to make 5 comparisons in order to find that out. And this makes a B tree, using a B tree, very easy. You don't have to compare with each and every node in order to find out whether your node exists or not. So this is what a B tree looks like. And the value right on top, this value is called the root node. And this value is called a leaf node, and every node that has something below it is called a parent node. So you can say that 30, 70, they are parents of 8, and 25, they are parents of 40 and 50, they are parents of 76 and 88. And you can say that 40 and 50, they are parents of all these 3 nodes right here. So that is what a parent node is. And the node that is coming out, that means the link is coming out from here, that node is known as a child node. So this is a child node of 40 and 50. So it contains of lots of parent nodes and lots of child nodes. And whatever you see here, down here, you can see that all these values, they do not have a link coming out. So these nodes, which are right at the bottom, and they do not have any children, they are known as the leaf nodes. So this is a common terminology for any kind of tree data structure that you study. It always has a root, and it always has leaf nodes and parents and children. But the properties that you see inside about how it is created, those are the properties of a B tree, where you are putting 30 and 70, 40 and 50. All these are properties of a B tree. So let's just once again look at these properties in a formal terminology. So in a B tree, every node has at most M children. And here M is defined by the person creating the B tree. So if you are creating a B tree, you are going to define what kind of a B tree you want to make. In this case, I have created a B tree where M is equal to 3 because each and every node can have maximum 3 children. That is why you can see this empty space here, because I can put one more node right here. So in this case, sorry, this is a B tree with M equal to 4 because each node can have maximum 4 children. So if this is your node right here, then it can have 4 children. So this is one child, this is the second child, third child. And if you add more values to it and happen to get a value here, then you can even add a 4th child. So on this level, I can have only 3 keys. These values in the boxes are called keys. So if I have 3 keys, I can have 4 children for this particular node. Every non-leaf node except the root has at least ceiling m by 2 child nodes. So we are not talking about the root node here. We are talking about every non-leaf node. What is a non-leaf node? We know that all these nodes right here are leaf nodes. So a non-leaf node would be a node that is here and here, but we are not considering the root right now. So these 3 nodes right here, they are non-leaf nodes, and they have at least ceiling m by 2. So in our case, m is equal to 4. So 4 by 2 is actually equal to 2. So at least they would have 2 children, and at least means 2 or more children. And we can verify that if this node is having 3 children, this also has 3 children, and this also has 3 children. So all are more than 2. The next is the root has at least 2 children if it is not a leaf node. So once again, the root, we can verify that it is having at least 2. That means 2 or more than 2 children if it is not the leaf node. And I'll show you with an example when a root can actually be a leaf node. And lastly, a non-leaf node with k children contains k minus 1 keys. So a non-leaf node, so let's pick this one. This is 8 and 25. How many keys does this node have? It has 2 keys, 8 and 25. So the number of keys are k minus 1 and the number of children are k. So how many children does this node have? It has 3 children, and because it has 3 children, the value of k is equal to 3. And therefore it has k minus 1, that means 2 keys. So it depends on how many keys are present. If there are 2 keys, this node will have 3 children. So that's how a B tree actually works. If there were 3 keys here, then this node would be having 4 children. Okay, so now I've explained the entire thing about a B tree. Everything that I could explain about a B tree is done here. So let's go ahead and create a B tree. And B trees can be of any type of order. And we are going to create one that is of order 3. So when you say that order is 3, then that means that that tree can have 3 children for each node. And we're going to see that with an example. So first of all, let's insert the value 1 inside the tree. And I know that one node can have 3 children. So that means in each node, there can be maximum 2 keys. So I'm going to create a box like this, and the box has space for two values. So if it exceeds 2 values, then I'll tell you what to do. Now in this case, there is first of all 1, and which we have inserted. And if you want to insert 2, then you can just insert it right there because there is space. Then let's insert 3. Now what happens is there is no space for 3. When there is no space, then we split the node. So if you look at this, there are 3 nodes here, 1, 2, and 3. And remember that you always insert in the sorted order. So you cannot just insert 3 anywhere you like. You have to insert it on this side because it's greater than 2. Now while inserting it, there's no space for 3. So you keep 3 here, and you need to split the node. So the node is always split from the middle. And in this case, there are odd number of keys present, so you can split it right from here. So now you're going to split it from the middle from 2, and it gets on the left side, there is 1, and on the right side, there is 3. So before this thing happened, before you inserted 3, this was the root node, and the root node had no children. So the root node was also a leaf node in that case. So this is the condition where the root node is having no children because there aren't that many keys possible. Now the root node is having 2 children and 1 key. So it is satisfying all the properties of a B tree. And on the left side, I've added 1 and kept the space for another 1. And on the right side, I've added 3 and there's space for another 1. Now let's insert 4. Where would you insert it? You would insert it right here because first of all, you will match 4 with 2 and you'll realize 4 is larger. So it has to go on the right side. Larger values usually go on the right side. That is by convention done that way. And then you would go on the right side and check with 3, and 4 is larger than 3 also. That is why you would place 4 next to 3 here. Now at this point, let's insert 5. So there is no space for 5 here, and that's why what you would do is try to shift 4 somewhere. You again have to do a split whenever there's no space. You know that 5 should come here, but there's no space, so you have to split. So in this case, again, when we have 3, 4, and 5, we always split from the middle because, like I said, it's a self-balancing tree. So self-balancing means it does not grow on one side, it grows on all the sides equally, on the left and right. So that's why we have to split from the middle. So now I'm going to split from 4, but I'm not going to do something like this is what most people do. A mistake that most people make is that they will put 4 here and they will create new nodes below 4 and attach 3 and 5 like this. But that's not how a B tree works. A B tree, first and foremost, tries to fill the levels that are available, and only when those levels are full, only then the B tree will create another level. And right now, the level above is not full. So 4 is going to go up there, and 3 and 5 will be attached to the left and right of 4 right here. So 3 to the left of 4 and 5 to the right side of 4. Now let's insert 6 into this. So 6 obviously is having enough space, and that's why 6 gets inserted right here without any problem. Then we insert 7, and once again to insert 7 you have to put 7 here, but there is no space. So once again, you are not going to create a level down, you're going to create levels upwards. A B tree always grows upwards, it does not grow downwards. And if you notice, then any kind of tree that grows even outside is always growing upwards, it does not grow downwards. So that's an easy way to remember that a B tree also grows only towards the top. So when we start from here, we have 5, 6, and 7, 3 nodes, and there's no space for 7, so we are going to move 6 to the top. But when we try to move 6 to the top, then it becomes 2, 4, and 6, and again, there's no space for 6. So what to do? We are going to move 4 to the topmost level. So now 4 is your root. On the left side of 4, there is 2. And on the right side of 4, there is 6. And for 6, on its left side, there is 5. And on its right side, there is 7. This is what your B tree looks like now. Now let's try to insert 8. To insert 8, it's very simple because I have space over here. So I'm simply going to insert 8 next to 7 because it comes in that order naturally. So 8 is inserted here. Next, we are going to try to insert 9, and once again, 9 would be inserted right here, but there is no space for 9 here. So we are simply going to move 8 to the top. So 8 is moved to the top. On the left side of 8, there is 7, and on the right side of 8, there is 9. And the last part is insert 10, and we know that there is a space for 10 here. So 10 is simply inserted right here without any problems. And this is your final B tree where you have inserted all nodes starting from 1 to 10. And in the next video, I'm going to explain a little more about B tree and some variant of B tree known as a B plus tree. So I'd suggest that you take a look at that too. So thank you for watching. See you in the next video.